Thanks, Ehor, and thanks, everybody. It's great to be here. Thanks for the invitation, and good to see all of our friends from Australia again. I am from Collins Aerospace. That used to be back in the olden days when we first started working with the SEL4 folks when they were NICTA back then. We were Rockwell Collins, and around 2018, we combined with United Technologies, and then the year after that, we combined with Raytheon, and so after a bunch of slicing and dicing and adding and subtracting and different things, we're now part of this company called RTX, which includes Raytheon and Collins Aerospace and Pratt & Whitney, who makes jet engines. So that's kind of the You Are Here thing. I'm part of our Applied Research and Technology organization. So we do a lot of research projects outside of the company and inside, but we engage with DARPA and NASA and the different service labs, AFRL, and those folks, and mostly in the U.S. But the company has expanded to have a much more global footprint. The people I work with most often on a daily basis are in Toulouse or in Rome or in Trento, not just in Cedar Rapids, Iowa, like it was in the olden days. So I'm going to talk to you about this new DARPA program. I'll give you some history on the PROVERS program, which stands for Pipeline Reasoning of Verifiers Enabling Robust Systems. I can never remember what that is. Everybody just calls it PROVERS, which is easier. Our project within that program is called INSPECTA, Industrial Scale Proof Engineering for Critical Trustworthy Applications. There's our mascot guy that kind of looks like Inspector Gadget, and so I don't know who owns him. I don't know if it's Nickelodeon or somebody like that. So just in case, we have as a backup our AI INSPECTA Gadget. So I want to give you kind of a background on what the PROVERS program is and our part in it, and some of the history leading up to that. And then I will go through the things that we are hoping to do in the program. So we're about 6 months in, so not a lot of really significant results to bring forth, but I'll try to give you an overview of what we're doing, there's a lot of different organizations, as you can see, that are part of our team in PROVERS, and give you an idea of what they're doing. And a lot of, probably 2/3 of those folks are actually here with us today. So every DARPA program has some concise elevator speech type objectives. This is what PROVERS is trying to do: to develop automated, scalable formal methods tools integrated into traditional software development pipelines, and enable traditional software developers to incrementally produce and maintain high-assurance national security systems. Okay, and so you see this traditional software developers occurring a couple of times. What does that mean? That means companies like mine that do defense and aerospace work. So the idea is to figure out how to more effectively engage with that industry so that they can use and take benefit from formal methods tools, including things like SEL4. So recently, as I'm sure everybody knows, these kinds of companies are all standing up formal methods groups, investing a lot, and getting great benefit from the use of formal methods. And so the question of PROVERS is, how do we help these kind of companies to do the same thing and achieve the same sorts of benefits in terms of cost savings and higher quality, more safe and secure systems, and generally encourage the adoption of formal methods in the defense and industrial-based development processes. Okay, that's the goal of this program. So some of the motivation behind it, a couple reports from the U.S. government in the last couple of years, and these are both really just pointing at the level of cyber vulnerabilities that are likely present in U.S. weapons systems. So this first one is actually saying that we don't know, because in most of the test and evaluation exercises that they do, they intentionally don't strongly red team the cyber aspects of weapons, because that takes away from the training aspects that they're actually trying to do. So they don't really know what they don't know in some sense. And then for some audits that have actually been done, they very routinely find mission-critical cybersecurity vulnerabilities. So they usually don't look, and when they do look, it's not good. So there's clearly issues here that need to be addressed as our weapon systems get more and more software-centric and potentially have more of these unknown, uncorrected cyber vulnerabilities. So this is a picture from another study that DARPA did a couple of years ago. And it was looking at this question of, the big tech kind of players and what they're doing with formal methods and why they've been able to make use of them versus where the DoD is and DoD contractors. And so it very roughly tried to, put the current state on these three axes of, some desire to adopt formal methods from a, what's the return on investment that you would expect to get, cost versus benefits. And then on the, the sticking out axis here, adoptability, which is really looking at the usability, scalability kind of questions. Is it reasonable for these industries to adopt formal methods? And then on the other axis here, the ability to adopt formal methods, looking at resources and workforce. Who are their employees? Are they prepared to do this? And so the general idea is that the big tech companies of the world are sort of in this blue blob where they've been able to do a lot of investment. They have a workforce that's prepared to maybe make more use of formal methods and are kind of moving up this scale here. But the DoD, while they might have some motivation in terms of the potential return on investment, they're blocked now, for better or worse, by usability concerns and where their workforce is at. And so the goal of Provers is to try to move this blob over to here, closer to the ideal spot where we've adopted and demonstrated the feasibility of using formal methods in defense systems. Okay, a couple other pieces of background here. You may have seen these two reports. These did show up pretty widely in the popular press. So back in February, there was this. These were both published by the White House Office of Science and Technology. This Back to the Building Blocks reports, and these are both fairly short, tens of pages. Looking at how do we make more secure, make our software more secure. And the funny thing was, this bit, the recommendation to use memory-safe language, memory-safe programming languages like Rust, got lots of airplay. Lots of, the articles mentioned that. But they almost universally missed that one of the main recommendations was use formal methods. That got almost no coverage at all in the press, but there it was. That was one of the main recommendations from this study. And I don't know if that's, for some reason, I don't know if it's because it was third on the list instead of first, or nobody knew what to do with it, or how to report on it, or whatever. But it was one of the main recommendations. And then this study on open source software and security had on one of its recommendations use formal methods, and in fact specifically calls out as an example the Provers program that is trying to address these kinds of concerns. So it's kind of cool to see formal methods showing up as a recognized important initiative by the U.S. government. Hopefully that will play itself out in the next couple of years by increased emphasis and requirements for adoption, funding, and things like that. We'll see. The last thing, this was interesting, it's obviously connected to those studies. So this was an interview, or actually a speech that Stephanie Tompkins, who's the head of DARPA, made earlier this year, talking about things like the HACMS program and use of formal methods on the Boeing unmanned Little Bird, which was our demo vehicle in that program, and really talking about the importance and the benefits of using formal methods in defense applications, and making the claim that we've done all these programs at DARPA and we've convinced ourselves that there's value here, let's, get off the stick here, and figure out what has to be done next to integrate formal methods into actual procurement programs. So there's this DARPA cyber resilience strategy that they're working on, where they're actually engaging with the Pentagon and the different service branches on, how do we make something out of this? How do we take the next steps? That they're talking about things like making use of formal methods a requirement of certain procurement programs or block upgrades to weapon systems or things like that. So it's great that that kind of thing is actually being discussed outside of this room, outside of academia, but in the Pentagon by DARPA and by the the Army, Navy, Air Force, and Marines. So what we're doing in the Provers program is 100% aligned with this effort. We're trying to help take these transition steps. This is always kind of annoying. This is how they tend to characterize use of formal methods, right? Hack-proof software, but nothing you can do about that. Okay, so the technical legacy of Provers goes back to the DARPA HACMS program, High Assurance Cyber Military Systems. This is where Rockwell Collins first started working with the SEL4 team, and so this was around 2013 that this started. This ran from like 2013 to 2017, and the goal was to show that it's possible to use formal methods to improve the cybersecurity of real aircraft weapon systems. So you can see we had this little quadcopter that we did a bunch of prototyping on, and did these really cool demos where we would show that you could launch on the unprotected system, cyber attacks while the thing is flying, take control of it, fly it over into enemy territory, and make it do bad things. And then we would reload all of our updated, verified SEL4-based software and show that those attacks weren't possible anymore. So that was like a real cool, tangible demo that people could relate to in a way that's showing them proof, or having them look at you sitting in front of your model checker wasn't as persuasive for some reason. But then we also did the same thing on a real Boeing helicopter, and they amazingly let us launch cyber attacks while this thing was flying. We didn't take control of where it flew, but we did. It's got this this fancy camera on the front. We were able to prevent that from being used. So if the thing is supposed to be doing a surveillance mission, we've prevented it from doing that. And we had another one related to the controlling the geofence of where the thing could fly, and breaking that kind of protection. And then updated all the software and showed that those kind of attacks were no longer possible. So super cool stuff. And then a couple years ago, we took this quadcopter, we dug it out of the box that had been sitting in for 4 years, and we took it to DEF CON and opened it up and invited all the hackers there to try to take control of the thing, and they weren't able to. So that was also a really fun demo. So the program that came after that was called CASE, Cyber Assured Systems Engineering. And there, the focus was not just a existence proof that you could use formal methods to do cool things on defense systems, but put together more of a tool suite to try to replicate that and take the next step. So we applied that there to the mission systems for the CH-47 helicopter, which was kind of the starting point for the Future Vertical Lift program with the Army, and did some similar kinds of cyber attack demos at our demo center in Huntsville, Alabama for the Army, and put together this pretty extensive collection of tools. They were based on the AADL modeling language to describe the system architecture, or do reasoning about the composition of components and how they interact and what properties they have, and then synthesize some new cyber components to filter bad messages or monitor the system and detect attacks, and a bunch of analysis tools for doing property verification, for generating assurance arguments, for checking information flow, And then this was all, there's a build environment that sits on to allow you to build an implementation that has the properties of the model that you had analyzed. And this is, all targeted at using what was then the CAM keys-based SEL4 system. All right, so that brings us up to today to the INSPECTA program that we're working on now. I thought I turned off my notifications. Okay, so this is the highlights that we advertise about the program, what we're trying to do here. So we're addressing the entire software stack from the requirements, system models, software components, code generation, the OS and the kernel, and introducing formal methods all throughout that throughout the stack. We're using compositional reasoning at the system level to kind of divide and conquer this big system and reason about components of it and how they interact. We've specifically chosen to look at the highest levels of assurance. I mean, you look at any given system, and there's a whole spectrum of is this thing really super safety critical, mission critical, or less so, and what methods are needed at those different levels. We're targeting the highest levels of assurance here just for our demo purposes. Our goal is to integrate all the tools that we're developing with current Collins workflows and automation processes, CI/CD processes, having as much as possible, cloud-based tools and automation of analyses. As you make some change to requirements or to code, you check it in, all the analysis goes and runs automatically, gives you, dang. I don't know how to turn that off. We're just going to live with it. I turned off Teams before I started here too. Obviously the goal is making formal methods accessible to non-formal methods experts. So that's kind of our test here, is that real live Collins system and software engineers who don't have any really deep formal methods education need to be able to use these tools. So we're leaning towards automated tools, and to the extent that we're using more sophisticated methods like theorem proving, the idea is to have things that have already been analyzed, verified, that we can make use of on a reusable component basis. The framework that we're building is designed to be adaptable and extendable. So if we have new languages, new requirements, new things that we have to make use of, we can do that, and we're applying them to actual aerospace products. So we'll talk about that here in just a minute. All right, I mentioned our team. This is kind of what everybody is doing. There's two main technology areas in the program. One focused on tool development, proof engineering, integration into workflows. That's this technology area 1. And technology area 2 is platform development, demonstration of the results. So on the TA1 area, we got Collins doing system requirements, model-based compositional reasoning, those kinds of things. Carnegie Mellon is doing software component analysis based on the Rust language, because we don't want to take advantage of all of the memory safety goodness from Rust, but be able to do analysis of the components that go into our architecture. Kansas State is focused on this build framework that takes us from models developed in the AEDL language, or now the SysML language that has way more traction in the DoD. So that's actually one of the things that we're doing in the program, generating code for SEL4 and potentially other operating systems. Our Proofcraft friends are working to make their proofs about SEL4 more robust and generalized, so it takes less work to, for example, move to a new hardware platform. UNSW Sydney is contributing a SAL4-based operating system and OS components with push-button verification. And then University of Kansas is helping us with component software synthesis, some AI-enhanced proof repair, and lifecycle attestation for gathering evidence about the workflow that we're producing. Well, then on the platform development side, Collins is working on what we call the restricted platform, which is an actual system. In this case, it's the U.S. Army Launched Effects, which is a tube-launched small UAV. I'll show you some stuff on that in a minute. And then DornerWorks is developing an open demo platform that's intended to mimic all the needs, mechanisms, the cyber assurance requirements that we will need for this real military system, but on an open platform that we can share with all of our university partners and publish about and everything else. So we'll talk about TA2 first and then go back to the TA1 tools. So this open demo platform, again, developed, supported by DornerWorks, kind of starting with some work that they did also with Collins on a CIBR program. And it's an unrestricted UAV mission software system. It's based on ArduPilot software. And it's really just, you have a host system, you send a flight plan to this thing, and it, figures out how to fly those waypoints, and then generates commands that then can be visualized in the simulation environment on the host. So really, we're just focused on this mission software that's running on this Zinc UltraScale board, ZCU 102. So that's just an open commercial board, but it happens to be like architecturally, and this the MPSOC component on there is the same one that we're using in our military platform. So it's very one-to-one compatible. There's also some other open hardware that we're using just for demo platforms with demos within Collins, based on a Raspberry Pi CM4 and a surrogate commercial UAV that we can fly around. So there's the software that we're ultimately focused on here is designed to be pretty platform independent, so it gives us a lot of flexibility for demos and the ability to run on less expensive open hardware. So this restricted or transition platform that is intended to be our real demo is based on the Army's launched effects system. It used to be called air launched effects, but they realized they actually want to be able to launch these things from the ground or from the air. So it's one of these small tube-launched UAVs, about maybe this diameter, and they come out of a tube and the wings fold out and it can go and fly around, and it's got a propeller in the back and can do different missions. So it can carry different payloads. A lot of times what they're doing is surveillance missions. There's a whole bunch of autonomy software that runs on these things, so they're designed to collaborate and talk to each other and go figure out how to cover an assigned surveillance area and send back imagery or targeting information or things like that, and adapt to threats and those sorts of things. And we've done flight demos at some of the big Army exercises in Arizona where they actually fly these things around. So I mean, this is a real thing, a real product. It's not deployed yet, but it's in sort of the demo phase where we're showing the Army capabilities and getting feedback, and they're deciding if they actually want to turn this into a program of record, which all indications are that they probably will. But it's intended to be relatively low cost, possibly attritable, so it doesn't necessarily have to come back, but it might, depending on the mission needs. Let's see if these work. Here's a couple of cool videos here. Am I just going to play? Ah, come on. Oh, here we go. Let's see if this one will play too. This will probably make lots of noise and stuff. Oh, I don't know. I wonder if I have the sound on. Yeah, I don't know. The sound's not coming through, but it's just like. You get it. But this is obviously a simulation on this side, but this is a pretty cool video. This is an Army video, and this is like some Raytheon videos, but it was showing like the ground launch thing. So, these could be kinetic, or it's like in this one, it's showing a surveillance mission where oh, you can hear some sound. Dramatic music plays. So this helicopter with the actual people in it can kind of hang back and send these things out to go into the dangerous area and find out where the targets are and send information back, and then from way back they can launch missiles that then go and blow up the bad guys and stuff like that. But so that's kind of the mission concept here. All right, you get the idea. But anyway, that's kind of what I think. When I think about this system, imagine the helicopter with the tubes on the side and these UAVs shooting out of it, and they're running SEL4. But right now, they just run Linux, right? They're doing capability demos just to show the functionality. And this is super common, right, for doing prototypes. Let's just get the software out there, show the customer what the thing can do, and then as people start getting interested, then they say, well, what about cybersecurity? What are you going to do about that? And our timing for this has been really awesome because we've been able to come in and say, hey, wouldn't you guys like to use this as a demo platform in our Provers program? Because then we'll take all your software and we'll run it on SEL4 and add a bunch of cyber guarding components that are verified, and we can address all of your customers' cybersecurity questions. Won't that be fun? And the answer is yes, it will. So anyway, we've gotten a lot of the timing has been really good for the program to get attention and engagement from the folks that are building a real system here. Okay, so that's TA2. Let's come back to TA1, the tool story. So I mentioned that we're trying to address the whole stack, and that's kind of what this picture is trying to show you, that this is kind of a normal development stack where we're starting with requirements and building an architecture in some modeling language, and then creating applications that populate that architecture, and then generating a bunch of the infrastructure code and configuration information that would target that should say like Microkernel, now the names keep changing, and running on the SEL4 kernel, right, and ending up with some sort of a binary. But at every level here, we have some formal methods tool that is helping us with the assurance questions here. So we've got this agree tool that we've been developing at Collins for a long time that does assume guarantee reasoning at the architecture level, and then we've got tools for analyzing the Rust components. That's where CMU is working. Actually, I can put there's all the organizations that go along with these tools. Kansas State, we've got Kansas and Kansas State on the program. It's not confusing at all. Kansas State is working on this Hammer tool for generating the components from the architectural model and generating OS configuration information. Kansas is working on both the synthesis of components from formal specifications and some AI-based proof repair, because every program needs to have some AI sprinkled into it. And then the UNSW and Proofcraft folks working on the SEL4, either verifying OS components of drivers, things like that, or working on generalizing and robustifying the SEL4 proofs. And there we got our DornerWorks folks helping us with the build of the open platform. So that's where everything is supposed to fit together. And then, so it's not just the individual tools, but trying to produce this integrated CI/CD pipeline workflow. So this is kind of how these things fit together. Traditionally, you'll have these different containers that you can stand up for doing testing or generating certification information or documentation, and then other, building the code. We're adding, other containers that have cloud-based analysis tools that we'll call the ProofOps container. But the idea is that these folks on this inner loop are the engineers that are trying to build a real system. They're interacting with all these tools that are generating the different artifacts that are produced for code, analysis results, and then any other instrumentation usage data that we want out of this. through this, and then visualizing it through this assurance dashboard, which is kind of extending some of our current metrics displays back to users. And then the outer loop is all the tool developer people that are getting a lot of the same information and using that to make improvements and extensions to our tools and learning, where are the barriers, how do we make this tool more usable, and make improvements to the tools themselves. So there's sort of this inner loop with the product engineers and the outer loop with the tool developers. And this is just a mock-up of this assurance dashboard. But the idea is, you could select, any of these different operations that are going on and gather the metrics and the status and, harvest all the information out of GitHub about what's been checked in or not and what properties are passing or not passing and display it in a concise way. So that's kind of the workflow objective in the program. Okay, so I will quickly run through some of the individual tools here, and fortunately a lot of the people that are working on some of the detailed stuff are actually here in the audience, and if you have any more questions that I can't answer, we can probably get them to help us a little bit. But the Collins part of this is kind of at the system modeling level, and our goal is to do reasoning about the architecture models and how components in those architectures interact to satisfy the system level properties. So specific things that we are working on here is extensions to this agree language to make it more usable, adding a better graphical interface that helps people to walk through counterexamples. So agree is fundamentally a model checker underneath. We get counterexamples that we can play back and visualize in the architecture to help engineers understand when properties don't work, what's gone wrong. We've done things like agree originally was very deeply embedded into the Eclipse environment because that's how you did AADL models. We've extracted it from that, created a headless version that's more compatible with integrating into a current CI/CD process, and we have a version now that runs in the cloud and it's not connected to any particular development environment. And then one of the other important things that we're doing, I mentioned this before, we've for many years been using the AADL language, the architecture analysis and design language, and there's really good reasons for that. In particular, it had a very well, it's an SAE standard. It has a very well defined semantics, though although previous, not in the past not a formal semantics, but a very good description of what the model should do when it executes. So there is a definition of the runtime behavior for an AADL model, and a textual representation that we could more easily reason about. Unlike SysML, which was essentially a drawing tool and didn't have any runtime semantics with it and kind of is intended to let you do prototypes at a higher level, but it doesn't let you make claims about I built this model and here's what I expect it to do at runtime. Really, I mean, there's some of the behavioral specs like state charts and activity diagrams and things that do have meaning behind them, but not at the same level as AADL is targeting distributed embedded real-time systems. So some of that is changing with SysML v2. There's a committee in OMG that's developing this, and their whole objective is to kind of merge the goodness of AADL into the backside of SysML. And so there is a textual representation which looks suspiciously like AADL, and it has descriptions of what such models are supposed to do behaviorally at runtime. So that's all great, and the real reason that's good is this has always been a usability / adoption barrier for the work that we've been doing. So we needed to have languages that we could reason about, but when we go to all of our DoD customers, they're all using SysML, and they have no idea what AADL is, and they don't want to change, blah, blah, blah. So this is sort of now finally our way forward to bring in the goodness of the formal analysis tools and connect it to SysML tools that our customers are more familiar with and more willing to use and adopt and actually interested in doing model-based system engineering. So a lot of what we're doing is just trying to update these tools, retarget to SysML v2, and that has implications down throughout the rest of the stack here. So I mentioned before some of the other things that we're doing are integrating these tools into CI/CD workflows. This is definitely the way we build things now inside the company, but we've got initial prototypes where we can have analysis tools run automatically when we check things in. We have workflow automations handled by GitHub Actions. The agree output comes out in JSON, and we can more easily parse that. I mentioned that we implemented this command line version of agree, and all the tools that I'm talking about here are all open source tools, and there's links, and you can go and play with them if you want. So this is just it does all the usual stuff, like when property fails, it sends you emails and tells you what's gone wrong and things like that. So pretty cool. We'll keep doing more and more of that. The Carnegie Mellon work is, since one of the things that we're doing here is in some of the past programs, most of the component code we had built was in C. We're trying to switch most everything over to Rust. And so as part of that, we wanted to have a verification environment targeting Rust. So this is what our friends at CMU are doing for us. This is Mariah Huell and Brian Parno primarily. So Brian's got this tool called Vera, so it's got Lean on the back end, and can do all kinds of cool analysis work on Rust. So one of the things that we're trying to do now is connect the contracts, the assumed guarantee contracts that we have in our system models, connect those to contracts on the Rust components that then can be verified by Verus to show that everything fits together. Kansas State is kind of at the center of a lot of what's going on here. They have this framework called HAMMER, which is high assurance modeling and rapid engineering for embedded systems. And this is really what gets us from this model with the component code down to something that can run on SEL4 or other operating systems if we want to target them. So it takes the models currently from AEDL. They are also updating all their tools to take in SysML v2 models at the top level and do the same sorts of functionality, generating the all the code for the interfaces that connects these components together and causes them to decides when threads should run and generate all the configuration information for SEL4, or you could just run these things in simulation on the JVM or Target Linux if you're, if that's what you want to do. So the idea is that that this is very a very componentized framework, so that the changes to be made to target another OS don't affect the the whole HAMMER stack. This picture kind of shows you if you have components that are interacting here, HAMMER takes information from the architecture model and generates all these different interfaces at the code level that take you from AEDL representations of data in and out of ports through SEL4 mechanisms previously through camp keys, now through Microkit for how these things interact, and then also sets up each of these functions here as a component that then runs on SEL4. So a lot of their work is switching over from C to Rust, from AEDL to SEL4 to AEDL to SysML v2, and from camp keys to Microkit. The Proofcraft work here is focused on making SEL4 proofs less dependent on experts for maintenance and extensions. So they, not really jokingly, say that part of the goal here is to put themselves out of business, give themselves less work to do, and that this takes a couple of forms. One is when you think about moving from one platform to another, instead of having to redo all the proofs, the idea is that the proofs can be parameterized, proved once against some conditions on those parameters, and then for each new, if you go to a new platform, you just, all you have to do is extract the configuration parameters and check whether they satisfy these conditions to know whether the proofs are gonna work or not. We've already been able to show that this is true on some of the platforms that we're interested in. So, things that, might take months before to do this port now take potentially 0 time or some small integer number of hours to actually check the parameters. Then there's another line of work that's making the proofs more agile and generic. So trying to split out what are the generic architecture independent parts of the proofs that don't have to change and separate those from the architecture dependent parts so that you know what has to change when you go to a new processor architecture. So the idea is the net result is to really have the proofs be more scalable, usable, much more, less cost to adapt to a new hardware architecture or platform. On the UNSW Sydney side, they are focusing on, and I'm sure we'll hear more about this later, and we have at previous conferences, the Lions OS, which is a new SEL4-based OS developed by UNSW. It's highly componentized and intended to make it easy to verify the individual OS components running in user space that you need, leveraging as much as possible push-button verification techniques. So this is what we're targeting for our the demonstrations that we're using. And then finally, the University of Kansas is contributing in a number of areas. So they've got some work on ML-enhanced proof repair to make it easier to, they do a lot of their work in COC now on attestation mechanisms. And so there's been some really interesting experiments that they've done jointly with Collins on use of large language models to come up with updated proofs when you make changes and to reduce the amount of effort necessary to update a proof. The main part of their work is focused on evidence protocols, so taking the attestation mechanisms that have been applied for assurance of remote computing platforms and apply those to the lifecycle development processes to gather, manage, and verify the evidence that's produced throughout the development process, and help us to collect that and display that as part of this assurance dashboard that I was talking about. And then they're also working on verified synthesis, taking some of the components like we did in CASE, where we want to add filtering and monitoring components, have a formal spec for those, now generate Rust components implementing those formal specifications. Okay, that's the whirlwind walkthrough of all the different verification technologies in our stack. But to wrap up, the workflow and tools here are addressing the whole stack, top to bottom, building on the best available technologies that we have access to and leveraging our experience from some of these previous programs as a starting point, integrating these tools into Collins workflows with as much automation as we can, and applying these to the Collins Launched Effects mission computer to enhance its cyber resiliency, to demonstrate the usability, the practicality, and the effectiveness of formal methods, and in the end, making formal methods accessible to non-formal methods experts within our company and other companies like ours. So there you go. Our research products end up on this loonworks.com website, and there's an introductory INSPECTA page that I just added, but that's where we'll eventually add links to all of the code repositories that we're developing and will be accessible throughout the program. That's it. Thanks.
Thank Thanks, Darren. So we've got a couple of minutes for questions. So if anyone has a question, we'll take 1 or 2 questions, and then we'll break. Please.
In one of your first slides, you mentioned that. In one of your first slides, you mentioned that companies like Google and Apple had highly skilled workforce, yet defense companies didn't have. They had limited workforce.
Formal methods,
Yeah,
skilled workforce, yeah.
So my question is, like, what do you think that is? And is the situation improving or worsening?
So that state is because those companies, Google, AWS, or whatever, made a conscious decision to start building up these formal methods heavy groups to address specific problems that they had. And that is, for a variety of reasons, not happened in the defense and aerospace industry. And some of that has been, I mean, there's historical reasons for that. A lot of it has to do with, understanding what's possible. We're also, I mean, both defense and aerospace are very conservative and slow to change, and we can't move fast and break things, because that would be really bad. I mean, it's one thing if your web server crashes or Facebook doesn't work or whatever. It's really bad if your, missile defense system doesn't work, or if your, 787 doesn't fly like it's supposed to. So by nature, it's a slow-moving industry, and we've relied on other, very test-heavy approaches to assurance. But, as complexity grows and grows, that's where we're kind of hitting the limits and needing, I would say, to turn to formal methods and formal methods-based technologies and software systems that allow us to retain the same level of safety and security. So, I mean, short answer is we're just big and slow, and it takes time to change, and we need to see examples that it's possible. And that was part of what the DARPA was trying to show here, is that, hey, this is happening in other industries. How do we take the slow, conservative defense industry down the same path? How do we help them to achieve the same benefits?